imagine, for a moment, pulling back from the Earth, back past the Moon, past the pale rings of Saturn, past the last cold planets of our solar system. Keep pulling back until the Sun itself becomes just one small light among billions. Keep going until our whole galaxy shrinks to a soft spiral of mist. And still, keep going, out past the local group of galaxies, past clusters that hold thousands more, until the view opens onto something even larger, a structure so vast it has no proper name in everyday speech. Scientists call it the cosmic web. From far enough away, this web looks almost alive. Long shining strands of galaxies stretch across the dark. Bright knots gather where the strands meet. Between them lie enormous quiet spaces, mostly empty, where almost nothing shines at all. These are the voids. The pattern is not random. It has shape, it has rhythm. It looks, if you squint, a little like the froth on a still pond, or the fine bones inside a bird's wing. And here is where the mystery begins, that gentle, sprawling pattern of galaxies you are picturing. The filaments, the walls, the empty rooms of the void, did not simply grow on its own. Some of it, perhaps a great deal of it, was shaped by sound, not sound the way we know it, not something you could hear with an ear, but real pressure waves, ancient ones, that rolled through the young universe when it was still hot and thick and glowing. The cosmos, in its infancy, rang like a struck bell, and the ringing left marks that we can still trace today, printed faintly across the sky, hidden in the way galaxies gather and cluster and drift. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. The question at the heart of tonight is a quiet one. How did those first pressure waves, rippling through a sea of light and matter long before any star was born, freeze into the great pattern we see now? How did a sound become a shape? And what do the faint fingerprints of that ancient ringing tell us about physics we may not yet understand? There are theories, and we will sit with them slowly. Some researchers believe the standing echoes of these early waves have given us a kind of ruler in the sky, a length we can measure between clusters of galaxies, a length that should always be the same wherever we look. Others wonder whether that ruler is truly as steady as we hope. There are small disagreements, small tensions in the numbers, that hint at something missing in our picture. Perhaps the ruler is slightly warped by dark energy in ways we have not yet learned to read. Perhaps it is warped by dark matter. Perhaps the very earliest whispers of the universe, from a time even before the ringing began, are still hiding inside the pattern, waiting for a sharper ear. For now, though, let the picture settle. Picture the web again. Silver threads on black velvet, great slow rivers of galaxies drifting along invisible currents, vast, soft, empty rooms where light barely travels. And imagine that if you could rewind the whole thing, run the cosmic film backward for nearly 14 billion years, you would see those threads pull together, tighten, brighten, until the whole universe glowed evenly, a hot pink fog with no galaxies inside it at all. And inside that fog, waves, real waves, ripples of pressure moving outward from every tiny disturbance, at nearly half the speed of light, singing through the young cosmos in a chord no ear has ever heard. Then, quite suddenly, the fog cleared. The waves stopped, and whatever pattern they had made in that moment was locked into place, like footprints frozen into cooling stone. Everything we see tonight, every galaxy, every cluster, every gentle strand of the cosmic web, grew inside those frozen ripples. We do not fully understand this, not yet. We know pieces, We can measure some of the fingerprints. We can point our telescopes at millions of galaxies and see the faint spacing they still remember. But the deeper questions, why the ruler shifts, what the earliest waves were made of, what physics still hides inside the pattern, remain gently, beautifully unresolved. So tonight, we will drift slowly through this idea. We will not solve it. We will only wonder about it, quietly, the way you might wonder about the shape of the clouds. A universe that once rang like a bell, a song that ended before the first star was born, and a faint ancient echo still humming softly in the arrangement of everything you see. Before there were stars, before there were galaxies, before there was even the idea of a night sky, the universe was a fog, not a fog of water like the kind that drifts through a valley at dawn. This was a fog of light and matter, mixed together so tightly that they behaved as one single thing. To picture it, imagine trying to see through the inside of the sun. That is close to what the whole universe was like. Everywhere, all at once. This fog filled every corner of space. There were no empty rooms in it. There was no outside to look in from. The fog was space, and space was the fog. It had no center and no edge, and it was hot. Not warm like a summer afternoon, and not hot like an oven. It was hot in a way that atoms cannot hold themselves together. At those temperatures, the tiny parts that make up matter were torn apart and set loose, drifting freely inside a bright, glowing sea. The fog was made mostly of two things. There were the tiny bits of matter, mostly protons and electrons, which are the small pieces that later go on to build atoms. And there were photons, the little packets of light. In our world, today, light travels through empty space and reaches our eyes without much fuss. Back then, light could not travel at all. Every time a photon tried to move, it bumped into a loose electron and bounced away. Then it bumped into another one, and another. The whole universe was blindingly bright, and yet it was completely opaque, because no light beam could ever cross more than a tiny distance before being scattered again. This period lasted a long time by human standards, though it was short compared to the age of the universe now. For about 380,000 years, the cosmos stayed in this glowing, foggy state. To put that in perspective, our sun is about 4.6 billion years old. The whole fog era would fit into a sliver at the very start of the universe's life, less than 1/100% of its history so far. And yet, everything we see today, every galaxy, every star, every planet, has its roots in what happened during that brief, luminous childhood. The temperature during this time cooled slowly as the universe expanded. Space itself was stretching, and as it stretched, the fog thinned and cooled the way steam cools when it drifts out of a kettle into a wider room. In the earliest moments, the fog was hotter than the core of any star. By the time the fog began to clear, it had cooled to about 3,000 degrees, which is hotter than molten iron, but cool enough for the parts of atoms to finally find each other and settle down. The scale of this fog is hard to hold in the mind. It filled the entire observable universe, which today stretches across roughly 93 billion light-years from one side to the other. Back then, the same amount of stuff was packed into a much smaller volume, because space had not yet expanded to its current size. So, the fog was denser than air, in some sense, though it was also nothing like air. It was a soup. It was a plasma, which is the fourth state of matter, hotter and wilder than any gas. There was no sound in the sense we usually mean it, because there were no ears, and no air, but sound, in physics, is really just a wave of pressure moving through some kind of medium. And the fog was a medium, a very strange, very energetic medium, but a medium all the same. Anything that pushed on it could send ripples racing through it. And there were things pushing on it. Gravity was pulling matter together into little clumps. Radiation was pushing back outward with tremendous force. This tug of war set the whole cosmic fog trembling. That trembling is the beginning of our story. The fog rang. It rang for hundreds of thousands of years, gently, at scales so vast that a single wave could stretch across regions larger than any galaxy that exists today. What the fog was doing during that long glowing infancy is something we can still hear echoes of, faintly, in the arrangement of galaxies around us now. How those echoes formed and what they became is the mystery we will sit with tonight. For now, it is enough to picture the fog itself, bright, dense, everywhere, trembling. A universe that had not yet learned how to be quiet. To understand how the ringing began, we have to go back further still, into a moment when the universe was smaller than a soap bubble and far hotter than the heart of any star. In that first flash of existence, space itself was expanding at a speed the mind cannot picture, and within that expanding heat, tiny bumps and dimples appeared. No one knows exactly why. One idea, favored by many, is that ripples from an early growth spurt called inflation were stretched from something smaller than an atom into ripples wider than galaxies. Another view suggests the ripples came from processes even older than inflation, from physics we have not yet named. Both possibilities remain open. Whatever their source, these tiny bumps were the seeds. There were places where the hot fog was ever so slightly thicker, and other places where it was ever so slightly thinner. The differences were fantastically small, perhaps 1 part in 100,000. Small enough to be almost nothing, large enough to change everything. Once those seeds existed, two forces began to argue with each other across the entire cosmos. Gravity wanted to pull the thicker spots inward. It tugged at every particle in the hot fog, trying to gather them closer. But the fog was not just matter. It was also flooded with light, a fierce sea of photons pressing outward in every direction. This pressure of light pushed back against gravity, trying to smooth the thick spots flat again. That push and pull is the beating heart of the story. Where matter tried to fall in, light tried to push it out. Where matter tried to gather, radiation tried to scatter it. This tug of war did not happen once. It happened everywhere, all at once, across the whole young universe. And out of that argument came something wonderful. Waves. The thick spots became the centers of ripples. Each seed sent a spherical shell of pressure racing outward into the surrounding fog. Picture a stone dropped into a still pond. Only the pond is made of glowing plasma, and the stone is a tiny bump in the density of that plasma. The wave that spreads out is not a wave of water. It is a wave of squeezed and stretched matter, moving together with the light that pushes it. A pressure wave, a sound wave in the truest meaning of the word. These waves moved at astonishing speeds in ordinary air on Earth. Sound crawls along at a few hundred meters per second. In the hot, radiation-soaked fog of the young cosmos, sound moved at more than half the speed of light. The medium was so dense with energy and so tightly coupled to the flood of photons that a pressure ripple could cross vast stretches of space in what felt like a heartbeat. For hundreds of thousands of years, this went on. Every tiny seed became the source of an expanding sphere of sound. And because the universe was full of seeds, it was also full of spheres. Ripples overlapped ripples. Waves crossed through waves. The whole cosmos rang, quietly and continuously, like an enormous bell that had been struck in a million places at once. There was no one to hear it, of course. Sound needs something to travel through, And back then the something was everywhere. But if a listener could have existed, they would have felt the universe humming in their bones. A low, steady chord, spread across every direction, made from the argument between gravity and light. We know this happened because the pattern of those waves left fingerprints we can still see. The tiny temperature differences in the oldest light of the sky match, in exquisite detail, what a fog of pressure waves would produce. And the way galaxies are arranged today, in gentle preferred distances from one another, matches the size those spheres reached before the ringing ended. Two very different measurements, taken with very different tools, both point back to the same slow, patient song. Yet the deeper origin story is still unfinished. We can trace the waves back to the moment the fog was hot and dense enough to sing. What we cannot yet do is trace them all the way back to the seeds themselves. Some researchers believe inflation planted them cleanly in a single burst. Others suspect the pattern hides small irregularities that would point to something stranger. The evidence so far is consistent with the simplest picture, but it is not yet strong enough to rule out the alternatives. So we sit here at the birth of the song, listening for what the first note was really made of. To understand the sound waves that shaped everything, we have to look closely at what the early universe was actually made of. It was not empty. It was not quiet. It was a thick, glowing soup, and every ingredient in that soup was pushing or pulling on every other ingredient. The song of the young cosmos came from this tension, this quiet argument between the things that wanted to gather and the things that wanted to fly apart. The first ingredient was ordinary matter, though in a form we rarely see today. Protons and electrons drifted freely, unable to join into atoms because the heat kept knocking them apart. These are the same particles that now make up your body, the walls around you, the water in the oceans, the iron deep in Earth's core. Back then, they had no home. They floated in a sea of light, waiting for the universe to cool enough for them to settle. Mixed in with the protons was a small helping of helium nuclei, forged in the first few minutes after the beginning. A trace of lithium hidden there too. This is nearly the entire recipe of ordinary matter in the young cosmos. Every heavier element you know, every carbon atom in a leaf, every gold ring, every calcium bone had to wait for stars to be born and to die. In those early moments, the universe had almost no chemistry at all. It was hydrogen, helium, a whisper of lithium, and light. The second ingredient was that light itself. Photons streamed through the plasma in staggering numbers, far more numerous than the particles of matter. For every proton, there were roughly 1 billion photons pressing outward. This radiation carried real weight. It pushed, it squeezed, it shoved against anything it touched. In a plasma this hot, light and matter were locked together, colliding constantly, moving as one restless fluid. The third ingredient was gravity, quiet and patient. Ordinary matter wanted to fall inward toward any slight overdensity, any tiny clump slightly richer than its surroundings. Gravity was the voice that whispered, "Gather here, come closer, sink toward the center." It never stopped whispering. The fourth ingredient was the one we understand least. Dark matter, whatever it is, was already there, spread through the young cosmos in an invisible scaffold. It felt gravity. It did not feel light. Photons passed through it without touching it. This strange substance sat in the gravitational wells, tugging on ordinary matter. But it did not ring when the light pushed back. It was silent in the song, yet it shaped the stage on which the song was sung. So picture the argument. In one corner, gravity and dark matter pulled ordinary matter inward, trying to collapse it into denser and denser knots. In the other corner, the radiation pushed outward, refusing to let the matter fall, because light and matter were bound together. Whenever gravity squeezed a region tighter, the radiation inside grew hotter and pressed back with tremendous force. The region would rebound, then gravity would pull again, then the radiation would push again, in and out, a slow, enormous heartbeat spreading through the entire cosmos at once. This is what a pressure wave is. It is the pattern of squeeze and release moving through a medium. In the air of your room, such waves become the sounds you hear. In the plasma of the young universe, the same physics played out at a scale beyond imagining, with wavelengths as wide as galaxies would one day be. The connections here are quiet and strange. The hydrogen that would become your drinking water was already present, sloshing back and forth inside these waves. The helium that now floats in stars and balloons rode along too. Even the dark matter, whatever it turns out to be, was mapping out the deep wells that these waves would ripple across. Everything you have ever touched has some ancestry in that first argument between gravity and light. Every atom in your fingertip once traveled inside a pressure wave 100,000 light years wide. What remains unresolved is subtle but important. We know the ingredients in broad strokes. We do not know what dark matter truly is. We do not know whether the balance between radiation pressure and gravitational pull was exactly as our equations describe, or whether some small extra ingredient hides in the mix. Some researchers wonder if a light, unknown particle rode along with the photons. Others suspect the recipe is complete and only our measurements need sharpening. The song was real. The instruments that played it are still partly hidden from us, and that quiet uncertainty is part of what draws us back to listen again and again across the empty spaces between the stars. Picture the infant universe as a vast ocean of glowing fog, and then imagine two great hands pressing against each other inside every drop of it. One hand is gravity, patient and heavy, always trying to pull matter together into clumps. The other hand is radiation pressure, the outward push of light itself, hot and fast and restless. These two forces met everywhere at once, and neither could win. Their long, quiet struggle is what made the sound. Gravity, in this early age, was the softer of the two. It reached out from every tiny, overdense pocket, every slightly thicker patch of the hot plasma, and gently pulled matter inward. If gravity had been alone, the universe would have collapsed into lumps almost immediately. But it was not alone. In that dense fog, photons, the particles of light, were trapped, bouncing off free electrons trillions of times a second. They could not travel far. They pressed outward with every bounce, and where matter tried to gather, the light beneath it grew hotter and pushed back. This push and pull is the heartbeat of the story. Gravity squeezes a region. The trapped light heats up as it is compressed, and its pressure rises. The rising pressure shoves the matter back outward. The region expands, cools, and gravity begins to pull it together once more, in and out, like the slow breathing of something enormous. Each cycle sent a ripple racing outward through the plasma. Each ripple was a sound wave, and these were not ordinary sound waves. In the air around us, sound moves at a lazy pace, a few hundred meters a second. In the primordial fog, the pressure was so extreme, the mixture of matter and light so tightly coupled, that these waves moved at more than half the speed of light. The universe was ringing at a speed we have no everyday word for. A single wave born at one spot could reach nearly 500,000 light-years across in the blink of the cosmos. Yet the fog was so thick that the wave had nowhere else to go. It could not radiate away into empty space. It could not fade into silence. There was no empty space yet. There was no silence. That is the strange and beautiful thing about the sound that filled the early universe. It could not escape. It was trapped inside the very medium that carried it. Every ripple that started somewhere had to keep traveling, keep pressing, keep meeting other ripples, keep folding into the great ongoing hum. The whole cosmos was one closed instrument, humming to itself in the dark. Gravity kept doing its slow work through all of this. It was not silent. It sculpted the deeper, longer notes, the vast low tones that stretched across enormous distances. Radiation pressure sculpted the shorter, sharper notes, the tight little quivers within each denser pocket, and beneath both of them, another player was already at work. Dark matter, whatever it truly is, dark matter, does not feel radiation pressure. Light passes through it without resistance. So while ordinary matter was being pushed around by the sound, dark matter stayed put, quietly gathering into its own gentle clumps, forming a scaffolding that the ordinary matter would eventually settle into once the noise stopped. How exactly these three forces, gravity, radiation, and the silent tug of dark matter, balanced across billions of tiny regions, is a question we can only answer in broad strokes. The equations describe the average behavior beautifully. The fine details, the way each individual ripple interacted with its neighbors, the way the dark matter shaped the paths of the sound, remain a subject of ongoing study. Some researchers wonder whether we are still missing a piece of the puzzle. Others believe the standard picture is nearly complete, and only sharper measurements are needed. What is not in doubt is that the struggle lasted a long time by the standards of that young cosmos. For hundreds of thousands of years, the plasma rang and rippled, the sound waves crossing and recrossing themselves, laying down invisible patterns of slightly denser and slightly thinner regions everywhere. The universe was tuning itself, though no one was listening yet. There were no ears, there were no stars. There was only the hot fog, the pressing forces, and the endless soft hum of a cosmos that could not fall silent. And somewhere in that long ringing, the seeds of everything we now see were being pressed into place. Every galaxy cluster, every empty void, every great filament of the cosmic web owes its position, in part, to which way the sound was traveling at a certain moment, a moment that was still to come, a moment when the fog would clear and the ringing would freeze. For nearly 400,000 years, the young universe stayed too hot for atoms to hold themselves together. Picture a fog that fills every corner of everything, not a cool morning mist, but a searing, blazing haze made of loose particles and trapped light. Electrons drifted freely, protons drifted freely. Photons, the tiny packets of light, bounced between them like pinballs, never able to travel more than a short hop before slamming into another charged speck. Try to feel the temperature of it. At the start of this era, the whole cosmos glowed at temperatures far hotter than the surface of the sun. Think of the inside of a furnace, then multiply that heat many times over and spread it across every cubic inch of space. There were no cold pockets. There were no shadows. Every direction looked the same shade of blinding white. Then, slowly, the universe stretched. As it stretched, it cooled. This took time, but not the kind of time we usually mean. 400,000 years sounds long by human standards. It is roughly the span from the first stone tools to today, folded over and lived twice. Yet, in the life of the cosmos, it is barely a heartbeat, The universe has been around for nearly 14 billion years. Squeeze that into a single day, and the fog cleared before the first minute was done. When the temperature finally dropped to about 3,000 degrees, something quiet and enormous happened. Electrons slowed down enough for protons to catch them. They joined into neutral atoms of hydrogen and helium. The charged fog thinned, and once the free electrons were gone, the light had nothing to bounce off. The photons, trapped for so long, suddenly had clear roads in every direction. They streamed outward, and they have been streaming ever since. Scientists call this moment recombination, though the name is a little misleading. The particles were not recombining. They were combining for the very first time. But the word has stuck, and it marks the instant the universe went from opaque to transparent. It is the moment the cosmos, in a sense, opened its eyes. To grasp how strange this was, shrink the whole history of the universe into a single year. On this calendar, the Big Bang happens at midnight on January 1st. Recombination, the clearing of the fog, happens about 15 minutes later. Everything else, the first stars, the first galaxies, the birth of our sun, the rise of life on Earth, all of it fills the remaining 12 months. That first quarter hour holds the entire soundstage on which every later story would play. Now think about the size of things at that moment. The observable universe, the part we can see today, was compressed into a sphere roughly 1,000 times smaller in every direction than it is now. What is now billions of light years across was then only millions, dense, glowing, packed tight, and rippling through it were those pressure waves we spoke of earlier, still spreading outward at more than half the speed of light, still carrying the pattern of every tiny lump and hollow in the primordial soup. When the fog cleared, the waves stopped, not because they hit anything. They stopped because the medium they needed simply vanished. Sound needs matter it can push against. Once the plasma became neutral gas, the photons stopped shoving the protons around. The pressure that had driven the ringing evaporated. Wherever a wave happened to be at that instant, that is where it froze. Picture pouring syrup onto a plate and then, in a single blink, turning it to glass. The last ripple pattern is locked in place, exactly as it was. That is what happened to the sound of the early universe. Its final shape was captured, spread across the sky, and left as a kind of fossil. The scale of that fossil is hard to feel. Each of those frozen ripples spread outward from its origin for the full 400,000 years. Moving that fast for that long, a wave could travel about 500,000 light years by the time it stopped. Then the universe kept expanding, stretching that distance by a factor of roughly 1,000. Today, the same ripple spans nearly 500 million light years from crest to crest. A single note, 500 million light years wide. How the exact size of that frozen note connects to the galaxies we count today, and whether the note has been distorted by physics we do not yet understand, is a question still very much open. For now, let it be enough to hold the image in mind, a universe that once rang. A moment when the ringing stopped, and the silence, still spreading, still measurable, still waiting to be fully read. Imagine, for a moment, that you could float just above the surface of the young universe at the instant the fog cleared. You would not stand on solid ground. There is no ground here, only a vast, glowing sea stretching in every direction, brighter than any sunrise you have ever seen. The light does not come from above or below. It comes from everywhere at once, a soft orange glow that fills the whole sky like the inside of a warm lamp. This is the last moment the cosmos was opaque, and on this glowing surface, if your eyes were tuned just right, you would see the ripples. They are not sharp, like waves crashing on a beach. They are gentle, broad, slow swells of denser gas set against slightly cooler hollows. Picture the surface of a still pond after a stone has been dropped in, but frozen at the moment the ripples spread outward. Now imagine that pond is the entire sky, and the stone was dropped a very long time before, and the ripples have been growing outward at the speed of sound in a sea of light for hundreds of thousands of years. The color would be something close to a soft coral, a warm reddish glow with hints of gold. That is the color of a gas near 3,000 degrees, cool enough, finally, to let light slip through. Under your imagined feet, the plasma has just turned into simple hydrogen. It is calm now, transparent. For the first time in the history of the young universe, a beam of light can travel a very long way without hitting anything, and in that light, the pattern is written. The denser regions are a touch brighter, a touch warmer. The thinner regions are a touch dimmer, a touch cooler. The difference is tiny, only about 1 part in 100,000. If the whole surface were a smooth ocean, these ripples would be no taller than the thickness of a hair. Yet those small ripples carry the memory of every pressure wave that ever rang through the plasma. They are the last note of a song that will never play again. Some of the ripples are small, no wider than a village might be. Others are enormous, stretching across regions that would take light itself hundreds of thousands of years to cross. One special scale stands out among all the others. It is the distance a sound wave could travel from the beginning of time up to this exact moment of clearing. Researchers call it the sound horizon. That special ripple, that particular size, will show up again and again, printed like a watermark across the sky. If you could hover above this glowing shell and squint, you might see the pattern almost like a marbled floor. Warmer patches nestled beside cooler patches, faint arcs, soft rings, nothing sharp, nothing loud, just a quiet, endless texture spread across a sphere so wide that the mind cannot really hold it. And then, in an instant that is not really an instant, the light lets go. The photons that had been trapped in the fog for so long finally stream outward in every direction. They rush past your imagined body and keep going, carrying the pattern with them. Those very photons are still traveling today. We see them as the cosmic microwave background, stretched by the long fall of time into faint radio whispers rather than orange glow. But at the moment of release, the surface itself, the gas that made the ripples, does not vanish. It stays behind. It cools, it thins, it begins to feel gravity's slow pull. And here is where the mystery starts to take its shape. The frozen ripples in that gas are the seeds. Somehow, over billions of years, those gentle swells will grow into galaxies, clusters, and the vast web of matter we live inside now. How closely the pattern we see today matches the pattern printed on this glowing surface is one of the deepest tests we have of our understanding of the cosmos. Some researchers think the match is nearly perfect, and that any small mismatch is just measurement noise. Others wonder whether something between then and now, some unknown ingredient, has quietly bent the pattern out of true. The surface itself cannot say. It can only glow and cool and remember. So picture it once more before we drift on. A soft coral sky in every direction, a gentle marbling of warm and cool, a sound horizon written in light, and a silence that has just begun, holding within it every galaxy that will ever be. The ripples are frozen now. What they became is the question we are still trying to answer. Beneath the smooth glow of that ancient light lies something stranger. When you look at the sky through an ordinary telescope, you see stars and galaxies scattered against the black. Thus, if you could strip that view away and see only the faintest microwave hum coming from every direction, you would find a map of the young universe, a map of where the sound waves stopped ringing. This map is not painted in colors we can see. It glows in microwaves, a form of light too long and too cool for human eyes. And its glow is nearly the same everywhere. The temperature of this ancient light is close to 2.7 Kelvin, only a whisper above absolute cold. Across the entire sky, it holds that temperature with astonishing evenness, but not perfect evenness. That is the secret hidden in the depths when you look more closely. When you measure the light down to 1 part in 100,000, tiny patches begin to appear. Some spots are a hair warmer, others are a hair cooler. These are not random. They are the frozen ripples of the sound that once filled the plasma. To understand what these ripples show us, imagine dropping a stone into a still pond. Waves spread out in rings. Now, imagine a pond that suddenly freezes solid at a single moment. The rings stay locked in place forever. That is what happened to the young universe. The sound waves were rolling outward from every dense pocket of matter. Then the fog cleared, the pressure vanished, the waves stopped moving, and the pattern they had drawn was preserved in the light and in the matter itself. The first faint map of these patterns took decades to build. Early instruments could barely tell the sky apart from noise. Then came satellites that measured the microwave background with more and more care. Each one saw the same thing, but sharper. Each one revealed finer features. And in those features, scientists began to notice something unexpected. The warm and cool patches were not random in size. They came in certain preferred sizes, over and over again. This preference tells us that the waves had favorite notes, like a musical instrument. The young universe rang most strongly at certain frequencies. The largest patches matched the deepest note the plasma could produce before the fog lifted. Smaller patches match higher notes, the overtones of that first fundamental tone. Together, they form a kind of song, written in temperature across the whole sky. What that song means, however, is still debated in its finer details. The overall pattern fits the standard picture very well. Ordinary matter, dark matter, radiation, and a tiny bit of everything else combine to produce ripples of just the right sizes. But there are small oddities. Certain regions of the sky seem slightly cooler than expected. A large cold spot in one direction has puzzled researchers for years. One idea suggests it is simply a rare statistical fluctuation. Another proposes it lines up with an enormous void of galaxies, which could chill light passing through it. A third possibility, more speculative, wonders whether it hints at something even stranger. Perhaps a mark left by physics we do not yet understand. The map also carries a puzzle about how smooth it truly is. On the largest scales, the universe looks a little less bumpy than some models predict. Whether this is meaningful or just a quirk of viewing only one universe from one spot, no one can say for certain. We have only one sky to measure. We cannot rerun the early universe to check our answer. There is something moving about the fact that this map exists at all. Every satellite that has scanned this glow is really reading a photograph taken when the universe was 380,000 years old. The light has traveled for over 13 billion years to reach us. It carries no images of stars or planets, because none had yet formed. It carries only the faintest whisper of the sound that filled everything before there was anything to see. And beneath that whisper, deeper still, sit the seeds of every galaxy that would ever be. The warm patches, ever so slightly denser, would slowly pull more matter toward themselves. The cool patches, ever so slightly emptier, would grow into the great voids. The song had ended, but the melody, frozen into the fabric of space, was already writing the future. What remains uncertain is how faithfully we can read that first map. Instruments have limits. The sky is only so large, and between us and that ancient light lies billions of years of matter that may have nudged the signal in ways we do not yet fully account for. The map is there, reading. Every note it holds is still a work in progress. Everything in the universe seems to breathe. Stars pulse, planets turn, galaxies wheel through slow, patient orbits that take hundreds of millions of years to complete. It swelled and settled, over and over, in cycles so vast they filled the whole of space. To read those ancient cycles, we have to learn how to listen to a glow, the light left behind when the fog cleared. The light we call the cosmic microwave background is not a single flat sheet of brightness. Look closely, and it shimmers with tiny hot spots and cold spots. Those spots are the frozen echoes of the ripples that were still moving when the pressure suddenly dropped away. Each one is a snapshot of the last breath the universe took as a ringing plasma. Astronomers have found something wonderful in those spots. The sizes of the hot and cold patches are not random. They cluster around certain preferred sizes, like ripples on a pond, that keep returning to the same widths. When you measure how bright the sky is at different scales, you see a series of gentle peaks and valleys in the signal. Those peaks are the fingerprints of the sound cycles. They tell us how many times the plasma bounced in and out before the light was set free. The first peak, the loudest note, is the sound wave that had just enough time to compress once before the fog cleared. The second peak is the wave that compressed and then began to relax again. The third peak is the one that completed a full cycle and started a second squeeze. Each peak is a wave caught at a different moment in its own rhythm. Together, they form a kind of chord, a chord that rang through the young cosmos and then went silent all at once. Reading this chord is delicate work. The peaks are faint. The signal must be pulled out of the soft static of the sky. Space telescopes have spent years staring at the microwave glow to measure it. They have mapped tiny variations in temperature down to differences of a few millionths of a degree. From those maps, careful teams have measured the positions and heights of the peaks with remarkable precision. What those peaks tell us, roughly, is how much of the universe is made of ordinary matter, how much is dark matter, and how much is something else entirely. The height of the first peak whispers about the total curvature of space. The ratio between the odd peaks and the even peaks hints at how much normal matter was riding along with the light. The way the peaks fade at smaller scales suggests how thick the fog was before it cleared. Yet even here, in this careful reading of an ancient song, there are notes that do not quite agree. Different measurements, taken with different instruments, give slightly different numbers for how fast the universe is expanding today. Some values come from the microwave glow itself. Other values come from watching nearby stars and supernovae. The two numbers do not match as well as they should. This mismatch has a name. Astronomers call it the Hubble tension, and no one is sure what it means. One idea is that the difference is simply a measurement error, some small bias in one method or the other that will fade as our instruments improve. Another idea is that something unexpected happened to the universe between the moment of the last ripple and now. Perhaps a new kind of energy briefly pushed on the young cosmos. Perhaps our understanding of dark energy or dark matter is incomplete in ways we have not yet noticed. Perhaps the sound wave ruler itself has been subtly stretched or squeezed by physics we do not yet know. Cycles, then, are not only in the ancient plasma, they are in our own back and forth attempts to interpret it. Each new observation refines the shape of the peaks. Each refinement raises fresh questions. The song keeps arriving from the past. Our understanding of it keeps circling closer, then drifting back, then closer again. There is something soothing in that thought. The universe took its last breath as a ringing plasma nearly 14 billion years ago. Its final chord is still washing over us in the form of a faint, cold glow that fills every direction of the sky. We are, in a sense, sitting inside the echo of a sound that ended before there were any ears to hear it. And each night, as we sleep, the echo keeps arriving, patient and quiet, waiting for us to understand what it has been trying to tell us all along. Imagine a ruler so long that no hand could ever hold it. A ruler stretched across the sky, made not of wood or metal, but of the faint memory of a sound. This is the standard ruler hidden in the stars. It is one of the strangest tools in all of science, and it lives in the way galaxies choose to sit near their neighbors. To understand it, picture the young universe once more. A hot, glowing fog, sound waves rippling outward in perfect spheres, each one centered on a small clump of matter. When the fog cleared and the ringing stopped, those spheres froze in place. Each little clump found itself gently surrounded by a faint shell of extra matter sitting at a certain distance. That distance became the ruler. Today, if you look at any galaxy, it has neighbors. Some are close, some are far. Most sit at random distances, scattered through the dark. But if you count carefully, across millions of galaxies, a soft pattern appears. Galaxies are just a little more likely to have a companion sitting about 500 million light years away than at other distances. Not much more likely, just a tiny nudge. But the nudge is real, and it is the same everywhere astronomers look. That preferred distance is the frozen echo of the sound wave. It is the size the last ripple reached before the fog cleared. Every galaxy carries a whisper of it. Every cluster remembers where its shell of extra matter settled. And so, without meaning to, the galaxies of the sky have painted a ruler across the cosmos. We only had to learn how to see it. The gentle rule is this: wherever gravity gathered matter, a soft ring of companion matter formed at that special radius. Over billions of years, those rings pulled more gas and dust, and new galaxies lit up along them. So the cosmic web is not just a random spatter of bright points. It carries a hidden rhythm, a quiet spacing woven through the dance of every neighborhood. Astronomers call this pattern the Baryon Acoustic Oscillation, or BAO for short. The name is a mouthful, but the meaning is simple. Baryons are the ordinary particles that make up stars, planets, and people. Acoustic means sound. Oscillation means a wave that moves back and forth. So the whole phrase just means the sound wave in ordinary matter, still faintly ringing through the arrangement of galaxies. The idea that this ruler even exists is beautiful, and the idea that we can measure it is nearly unbelievable. To find it, teams of astronomers must map millions of galaxies. They must record the position of each one in 3 dimensions, then count pairs at every possible separation. Only after crunching all those pairs does the tiny bump appear on the graph. It is a soft rise, easy to miss, but once you see it, you cannot unsee it. It is a real feature of the sky. Here is where the mystery begins to sharpen. If we know the true length of the ruler from the physics of the early universe, and we can measure how long it looks from our vantage point today, then we can figure out how far away things are and how fast the universe has been stretching. This is why the ruler matters so much. It gives us a way to measure the cosmos without borrowing anyone else's yardstick. But different surveys, using different methods, seem to get slightly different answers. Some measurements suggest the universe is expanding a touch faster than expected, others suggest a slower pace. The disagreement is small, yet stubborn. Some researchers wonder if the ruler itself has been subtly stretched or bent by physics we do not yet understand. Others think the difference will vanish once measurements grow more precise. The question remains open. There is also a quieter puzzle. The ruler works best when we trust that space between recombination, and today has behaved in a smooth, familiar way. If something unexpected happened in the long, dark ages, some unknown field, some soft ripple of new physics, the ruler could be quietly telling us about that too. We just would not know how to read the extra whisper yet. For tonight, let the picture rest simply. Every galaxy has a favorite distance for its neighbors. That distance is the frozen size of a sound. The sound stopped ringing when the universe was very young, and the pattern has been drifting outward, softly ever since. The cosmic web is not silent after all. It hums in geometry at a scale so vast that whole galaxies serve as its notes. And the mystery is not whether the ruler exists. It clearly does. The mystery is what its slight, stubborn imperfections are trying to tell us. Somewhere in the darkness, at a distance so vast the human mind can barely hold it, there are pairs of galaxies that still remember the ringing. They sit apart from each other by about 490 million light-years, give or take. That number is not random. It is the frozen echo of a sound wave that stopped traveling almost 14 billion years ago. And once you know to look for it, galaxies across the entire visible universe seem to whisper the same soft preference for that distance. This is one of the strangest extremes in all of cosmology. A single sound wave, born in the first moments after the Big Bang, left its fingerprint at a scale so enormous that no telescope can capture it in one frame. To see it, astronomers must count millions of galaxies at once, and let the pattern rise out of the noise like a face slowly appearing in a crowd. The most extreme thing about this pattern is how faint it is. If you picked any galaxy in the sky and asked how far away its nearest neighbors sit, you would not notice the ripple at all. The signal only appears when you average across huge populations. It is a whisper of about 1% stronger clustering at that special distance. 1%. And yet, that whisper has been strong enough to shape entire chains of galaxies stretching across the observable universe. The largest galaxy surveys ever built exist mostly to hear this whisper. Some of them have mapped more than 2 million galaxies. Newer ones aim for tens of millions. Each galaxy is a tiny data point, and only when you gather enough of them does the ancient sound wave lift itself out of the static. It is a bit like standing in a stadium and trying to hear a single soft note played long ago by counting how the seats have been arranged. The oldest galaxies that carry this memory formed only a few 100 million years after the fog cleared. There, light has been traveling toward us for more than 13 billion years. When astronomers measure the acoustic ripple at those enormous distances, they are seeing the wave as it looked when the universe was still young, before dark energy had fully taken hold. Compare that to the ripple measured in nearby galaxies, and you can watch the ruler stretch across cosmic time. That stretching is where the deepest mysteries hide. The distance between those paired galaxies today should be a precise, predictable number, based on how fast sound moved through the primordial plasma and how much the universe has expanded since. Our different methods of measurement keep giving slightly different answers. The gap is small, only a few %, but it will not go away. Some researchers wonder if the ruler itself has been quietly distorted by physics we do not yet understand. Others suspect the problem lies in how we calibrate our measurements of nearby galaxies. The question remains open. Then there are the rarest galaxies of all, the ones that sit inside the great cosmic voids. These vast empty regions can span hundreds of millions of light years with almost nothing inside them. A single lonely galaxy drifting through such a void is one of the most isolated objects in the universe. And yet even that galaxy is not truly alone. The acoustic ripple influenced where it could form. Its very existence, or absence, is part of the frozen music. The fastest expansion in this whole story happened in the very first fractions of a second, when the seeds of the ripples were laid down. After that, the wave itself traveled through the plasma at more than half the speed of light, which is astonishingly quick for a sound. Ordinary sound in Earth's air moves about 1,000,000 times slower. This was a sound made of pressure in light and matter fused together, and it behaved in ways that no sound on Earth ever could. The coldest thing the story leaves us with is the silence that followed. Once the fog cleared and the ringing stopped, the wave was frozen in place. It has not moved as sound since. It only stretches now, quietly, as space itself grows larger. Every galaxy that carries the memory is carrying a note that no ear will ever hear again. What we do not know is whether the ruler is truly as reliable as we hope. If the early universe held forms of matter or energy we have not yet identified, the frozen ripple could be subtly off. Some theorists suggest exactly that. Others insist the standard picture holds. For now, the galaxies keep their ancient secret, and we keep counting them, hoping the pattern will finally speak clearly. If you could pull back far enough from our galaxy, farther than any telescope will ever carry a human eye, the universe would begin to look less like scattered dust, and more like a soft, tangled net. Galaxies do not sit in space at random. They gather along thin, bright threads. Those threads meet at glowing knots. Between the threads lie vast, quiet emptinesses, dark rooms of nearly nothing, some hundreds of millions of light years across. This is the cosmic web, and its quiet architecture may be the softest, oldest music ever written. The threads are called filaments. They can stretch for hundreds of millions of light years, made of dim galaxies, warm gas, and the mysterious dark matter we cannot see. Where several filaments meet, galaxies pile together into clusters, some holding thousands of member galaxies bound by gravity. Between the filaments, the great voids yawn open, so empty that a single galaxy inside, one might feel like the last light in an ocean of dark. And running through all of this, hidden in the spacing itself, is a preferred distance, a gentle rhythm, a soft note that no ear will ever hear. Astronomers have measured that rhythm when they map millions of galaxies and count how often two galaxies sit at a certain distance from each other. One distance shows up slightly more often than the rest. It is not a sharp spike. It is a small, gentle bump in the counts, near a scale of about 500 million light years in today's stretched universe. That soft bump is the frozen echo of a pressure wave that stopped ringing nearly 14 billion years ago. The web remembers. What makes this detail so beautiful is how quiet it is. If you looked at any single pair of galaxies, you would see nothing special. If you looked at 100 pairs, still nothing. You have to gather millions of them, and only then does the pattern rise softly out of the noise. like a whisper heard through a wall. The signal is only a small percent above the background. It took decades of careful counting before anyone was sure it was really there. The knots and filaments hold other quiet clues too. Galaxies inside clusters often line up along the direction of the filament that feeds them, as though they remember the current that carried them in. Gas flowing along a filament can be warmer than the empty voids, yet colder than the hearts of clusters. A middle temperature that leaves a faint fingerprint in the light of distant quasars shining through it. Some of this warm gas has only been mapped in the last few years, and much of it is still missing from our accounting. Where exactly it hides is one of the field's softer, patient puzzles. There is a competing way to think about the web's shape. One view says the pattern is mostly written by dark matter, which fell together under gravity and dragged the visible galaxies along its lines. Another view gives more credit to the ancient sound waves themselves, arguing that the ripple pattern set the stage before dark matter's slow sculpting even began. Most researchers suspect both are true at once, working together, but the exact share of the work each did remains an open question. The web we see is a duet, and we are still learning which voice sang which part. The voids are their own quiet wonder. They are not perfectly empty. A few faint galaxies drift inside them, isolated and slow to grow, since there is little nearby matter to feed them. Some researchers wonder whether these lonely galaxies look different from crowded ones in ways we have not yet fully measured. Others study the shapes of the voids themselves, since a void that started round should have stretched slightly as the universe expanded, and that stretch may carry its own record of dark energy's pull. There is also a subtle texture inside the filaments. Simulations suggest they are not smooth tubes but braided currents, with smaller threads twisting inside larger ones, gas spiraling gently as it falls toward the knots. Whether real filaments truly braid this way, or whether the simulations are painting a more elegant picture than nature deserves, is still being tested with careful observations of the faint gas between galaxies. All of these small details, the bump in the counts, the aligned galaxies, the warm hidden gas, the slow drift of lonely galaxies in the voids, are the fine grain of a pattern that began as sound. The web is not loud. It does not announce itself. It waits quietly for anyone patient enough to count and to listen and to wonder what else its soft geometry might still be trying to tell us. For most of human history, the sky above us seemed simple. Stars were scattered like grains of sand, and the space between them was thought to be empty. Astronomers assumed galaxies drifted through the dark in a random, gentle sprinkle. The idea that the universe might have hidden shapes, huge patterns woven through space, would have seemed strange even to careful observers just 100 years ago. The first hint of something larger came slowly. In the early 20th century, astronomers began cataloguing galaxies with better and better telescopes. They noticed that galaxies often gathered in small groups, and those groups sometimes gathered into clusters. But the maps were flat. They showed where a galaxy sat on the sky, but not how far away it was. Without distance, the deep structure stayed hidden. The tool that changed everything was redshift. When light from a distant galaxy is stretched by the expansion of space, its color shifts slightly toward red. By measuring that shift, astronomers could estimate distance. Once distance was added, flat maps of the sky became three-dimensional maps of the cosmos. And what those maps showed was quietly astonishing. In the late 1970s and early 1980s, a team of astronomers at the Harvard-Smithsonian Center for Astrophysics began a long, patient survey. Margaret Geller, John Huchra, and their colleagues measured redshifts for thousands of galaxies. They plotted them in wedge-shaped slices of the sky, Slowly, over years of quiet work, a picture began to emerge on the paper. The galaxies were not scattered evenly. They lined up. They formed long strands and sheets. Between those strands lay enormous rounded emptinesses, regions where almost no galaxies could be found. One of these voids was so large it stretched hundreds of millions of light years across. Another feature, a vast wall of galaxies, was so long that its full size could not even be measured within the survey. They called it the Great Wall. The reaction at first was disbelief. Many astronomers had expected clusters and groups, but not walls and voids on this scale. Some wondered if the survey was seeing some kind of illusion, an artifact of how the data was collected, but the pattern held. Other surveys, using other telescopes, found the same strange geometry. The universe, it seemed, had been quietly arranging itself into a lattice of light and shadow, and no one had noticed. As more surveys came online, the picture only grew richer. The 2-degree field galaxy redshift survey in the late 1990s mapped more than 200,000 galaxies. The Sloan Digital Sky Survey, which began in 2000, would eventually catalog millions. In their maps, the cosmic web became undeniable. Galaxies gathered along filaments, thin bridges of matter stretching across hundreds of millions of light years. Where filaments crossed, dense clusters glowed. Between them yawned the voids, dark and nearly empty, like bubbles in a sea of foam. For a long time, no one connected this web to the ancient sound waves of the young universe. That link came later, and it came from the mathematics of the cosmic background radiation. If pressure waves had once rippled through the hot plasma, then the places where those waves had been should still, in some faint way, favor the growth of galaxies. The prediction was subtle. It suggested a slight extra tendency for galaxies to sit at a certain distance from each other, a distance echoing the reach of the frozen sound. Finding that echo in the web took another 20 years of patient work. In 2005, 2 independent teams announced they had detected the faint signature buried in galaxy surveys. The peak was small. It could not be seen by eye in any single slice of the sky. It only appeared when astronomers averaged the distances between millions of galaxy pairs and looked for a tiny bump in the statistics. But the bump was there, right where the ancient sound wave said it should be. That discovery tied the walls, the voids, and the whispering filaments back to the ringing plasma of the infant cosmos. The web was not random. It carried a memory, and yet, even now, so much remains unclear. The web looks slightly different in different surveys. Some regions seem too empty. Some walls seem too dense. Whether these small mismatches are simple measurement problems or hints of physics we do not yet understand remains an open question. What is certain is that a few careful astronomers, plotting dots on paper in dim rooms, uncovered something no one had suspected. The universe had a shape, and that shape had once been sung into being by a sound that fell silent long before the There is something strange about the whole idea of listening for these ancient waves. The sound itself is gone. It has been gone for nearly 14 billion years. What rang through the young universe went silent the moment the fog of hot plasma cooled into clear gas, and yet somehow we can still find the shape of that final ring, frozen in the way galaxies are scattered across the sky. That single fact tends to catch people off guard when they first hear it. The waves did not leave a recording. They left a preference, a gentle bias in where matter chose to settle. If you pick any galaxy at random and then look outward from it, you are slightly more likely to find another galaxy at a distance of about 490 million light-years than at slightly shorter or slightly longer distances. Not much more likely. Just a whisper of a bump in the odds. That whisper is the last note of the cosmic bell. Most people assume such a subtle pattern would be impossible to detect, and for a long time it was. You cannot see the bump by staring at any single patch of sky. You cannot see it in any single pair of galaxies. It only appears when you count millions of galaxies and measure the distances between every possible pair. The signal hides inside a statistical haze, and only enormous surveys can pull it into view. There is another surprise buried in this. The ruler we are measuring is larger than almost anything the human mind can picture. A single Baryon acoustic ripple stretches farther than the width of most galaxy clusters. It is a feature of the universe so vast that no telescope can capture it in one frame. To see it, astronomers must build three-dimensional maps of the sky, plot the position of each galaxy in space, and then let a computer sift through the distances. The pattern only emerges from the collected whole. Something else tends to surprise people. The waves were never sound in the way we usually think of sound. In the young universe, the medium was so dense and so hot that pressure waves moved at more than half the speed of light. If you could somehow have stood inside that plasma and shouted, your voice would have raced outward at a speed no earthly sound could match. The physics is the same as the physics of a struck drum, but the numbers are wildly different. Ordinary intuition about sound simply does not apply. Then there is the matter of dark matter, which did not sing along. Ordinary matter felt the pressure of the light and bounced outward in waves. Dark matter felt only gravity and stayed roughly where it was. When the fog finally cleared, the ordinary matter froze in a thin shell around each original clump of dark matter. Every galaxy today carries this hidden double structure in its neighborhood, whether or not anyone living inside it ever noticed. It is a strange thought that our own Milky Way sits somewhere on the faint ripple pattern of a wave that stopped moving before the first star was born. One of the deepest surprises is that this frozen sound can be used as a measuring stick across billions of years of cosmic history. If we know the true length of the ripple, and we can measure how big it appears at different distances, we can figure out how much the universe has stretched since that light was released. This turns a ghost of a sound into a tool for measuring dark energy. Few people expect that a whisper from the plasma era would end up as one of our best clues about the fate of the universe. And yet, there is a catch that has begun to unsettle researchers. When we measure the expansion of the universe using the acoustic ruler, we get one number. When we measure it using the light of nearby exploding stars, we get another. The two numbers do not quite agree. This mismatch, sometimes called the Hubble tension, might come from a small error in one of the methods, or it might come from new physics operating somewhere between the frozen sound and today. No one is yet sure. That means the ripple is not just a tool. It is also a question. It behaves in ways that fit almost every prediction, and then, at the edge of precision, refuses to line up with other measurements. Some researchers believe the tension will vanish once the surveys grow larger and more careful. Others suspect the ruler itself is being subtly distorted by something we have not identified. Both possibilities remain open. For now, the strangest thing about listening to the ancient sound may be that it is still telling us something we cannot yet translate. Somewhere in the language of astronomers, there is a phrase that sounds almost like poetry. Baryon acoustic oscillations, 4 words for a ripple that never quite went away. Baryons are the ordinary particles that make up you, and the chair beneath you, and every star in every galaxy. Acoustic means sound. Oscillation means a wave that rises and falls. Put together, the phrase describes something quiet and strange. The pressure waves that rang through the young universe left a faint fingerprint on the way ordinary matter is spread across the sky. And that fingerprint, more than any other single clue, is how modern cosmology ties its many stories together. Think of it as a hidden thread. Pull on it in one place, and something moves on the other side of ideas. Pull on it near galaxy surveys, and it tugs at the cosmic microwave background. Pull on it there, and it tugs at the theory of dark energy. Pull on that, and it tugs at the expansion rate of the whole universe. Nothing in cosmology stands alone, and the ancient sound waves are one of the strongest reasons why. Here is how the thread runs. Long before there were stars, the young universe carried sound. When the fog cleared and light broke free, those sound waves froze into a preferred distance between clumps of matter. That distance became a kind of ruler laid across the sky. Today, when astronomers count galaxies in enormous surveys, they find that galaxies are slightly more likely to sit at that ruler's length apart than at any other distance. The old ringing is still there, buried in the pattern of where things live. That single ruler quietly connects to almost everything else we try to measure. Its length is set by physics in the first few 100,000 years. Physics we think we understand well, so we know how long the ruler was when it formed. If we then measure how long it appears now, at different distances across the sky, we can work out how much the universe has stretched in between. Sound waves in the young cosmos, in this way, become a tool for weighing the expansion itself. And the expansion is where things get interesting, because the universe is not stretching at a steady rate. Something is pushing it apart, faster and faster. We call that something dark energy, though the name is really a placeholder for our ignorance. The frozen sound ruler is one of the cleanest ways to study how dark energy has behaved over billions of years. If the ruler appears the size we expect at every era, dark energy is probably a smooth constant. If the ruler seems slightly off at certain distances, dark energy might change with time. Different galaxy surveys have hinted at both answers. The question is still open. The thread runs further still. The same sound waves that shaped galaxy positions also left ripples in the ancient light of the cosmic microwave background. Those two imprints, one in light and one in matter, should agree. When we compare them, we mostly find harmony, but not perfectly. The rate of expansion measured from the old glow and the rate measured from nearby galaxies do not quite match. This mismatch has a name, the Hubble tension, and no one is sure what causes it. One idea is that we are measuring something wrong. Another is that some unknown physics between the early universe and today has quietly bent the ruler. There is a real beauty in this web of connections. A pressure wave that traveled through hot plasma when the universe was a baby is now used to test theories about the deepest nature of space. A whisper in the fog becomes a measuring stick. A measuring stick becomes a probe of dark energy. Dark energy becomes a mystery about the fate of everything. It all links back to those first minutes of ringing, and yet the harmony has small dissonant notes. Different teams, using different galaxies and different methods, sometimes get slightly different values for the ruler's apparent length. These disagreements are tiny, but in cosmology, tiny disagreements are often where new physics hides. Some researchers wonder if the ruler itself is not quite as steady as we assumed. Others suspect that gravity behaves in unexpected ways on the largest scales. Still others think the differences will shrink as our surveys grow. For now, the sound waves keep singing across the data, connecting the earliest moments to the latest galaxies. tying light to matter, tying expansion to gravity, tying what we can measure to what we still cannot explain. The web holds together, mostly. Where it strains, we listen more carefully, hoping the strain itself will teach us something about the parts of the song we have not yet learned to hear. Something strange happens when we try to count the matter in the universe. We add up all the stars, all the gas, all the dust, all the glowing clouds that hang between galaxies. We measure the light they give off. We measure the shadows they cast. And when we finish the sum, we find that a large portion of the ordinary matter we expect to see is simply not there. This is not the famous mystery of dark matter, which is a separate puzzle entirely. Dark matter is thought to be something new, something that does not shine or scatter light at all. The missing matter we speak of here is ordinary. It is made of the same protons and neutrons that build your hands, the walls around you, the water in a glass. The old sound waves in the early universe tell us how much of this ordinary matter should exist. The cosmic microwave background gives us a very precise count. And when we look out at the sky today, roughly a third to a half of it seems to have gone quiet. Where did it go? That is the puzzle, and the answer, if we ever find one, may be tangled up with the same ancient ripples that shaped the cosmic web. One idea is that the missing matter is not missing at all. It may be hiding in long, thin filaments of very hot gas stretched between galaxies. These filaments are thought to form the skeleton of the cosmic web, tracing the paths carved by those frozen sound waves. The gas inside them may be so thin and so hot that it barely glows. It gives off a soft, faint light in the X-ray part of the spectrum. Our instruments have only recently grown sensitive enough to catch small hints of it. Some surveys claim to have found traces along the bridges between galaxy clusters. Others see nothing where they expected to see something. A different possibility is that the missing matter was pushed out of galaxies long ago by powerful winds. When stars die in violent explosions, they can drive gas far beyond the edges of their home galaxy. Over billions of years, this outflow may have thinned the gas until it drifted into the vast spaces between the web strands. If so, the matter is still there, just spread so widely that we cannot easily see it. Which of these two pictures is closer to the truth remains unsettled. It is likely both play some role, but the balance between them is still being worked out. The connection to the ancient sound waves is quiet, but important. Those pressure ripples set the pattern of where matter would gather and where it would thin out. The ridges of the ripples became the walls, and filaments, the troughs became the voids. If ordinary matter has slipped into the faint spaces between galaxies, it should follow the same pattern the ripples once drew. Some researchers have tried to use the shape of the cosmic web as a map, guessing where to point their instruments to catch the missing gas hiding along the filaments. It is a slow, patient search, and the picture keeps changing. Every year, new surveys refine the numbers. 10 years ago, the gap between expected and observed ordinary matter was wider. Today, small pieces have been recovered, faint glows detected in the right places, thin threads confirmed between certain pairs of galaxies. The universe is not staying the same in our minds. It shifts as we learn to see it better. The web is filling in, strand by strand, as if we were slowly turning up the brightness on an image that has always been there. Still, the counting is not complete, and there is a chance that the mismatch is telling us something deeper. If the missing matter cannot be found in filaments or halos or hot outflows, then perhaps our understanding of the early sound waves is slightly off. Perhaps the ripples did not set the balance of matter quite the way we assume. Perhaps something happened between the moment of recombination and now that we have not yet accounted for. It would be a small crack in a very well-tested picture, but small cracks are often where new physics enters. For now, the mystery sits gently in the background. Ordinary matter, made of the same stuff as everything we touch, seems to be scattered thinly through the cosmic web, following pathways drawn by sound waves that fell silent long ago. Some of it we have found, some of it we have not, and the search continues, slow and steady, as our telescopes grow patient enough to detect the faintest glow of a gas so thin it is almost nothing at all. There is something strange about the song that shaped the cosmic web. The part we can hear, in a sense, was made by ordinary matter, the protons, the electrons, the light itself. These are the pieces of the universe we know well, the pieces that glow and press and push against each other. But most of the matter in the young universe made no sound at all. It moved, it pulled, it gathered, yet it did not ring. We call it dark matter, and we still do not know what it is. We only know it by its silence. Ordinary matter in that hot early plasma was tangled up with light. Photons pushed against it, and it pushed back, and together they sang. Dark matter felt none of that. Light passed through it without a whisper. It sat quietly in the background, drawn only by gravity, unmoved by the pressure that made the waves. Picture the young universe as a glowing pink sea, hot and dense, threaded with countless ripples spreading outward from every small overdensity. Now picture, beneath that shining surface, a second layer, a colorless, invisible fog. It has no glow, it gives off no light, it does not scatter, it does not shine, it simply gathers, in slow, steady mounds, wherever gravity tells it to go. The sound waves ripple across the bright layer above. The dark fog below barely stirs. When the plasma cleared and the ringing stopped, the ordinary matter froze into shells, faint rings of extra density, spaced about 500 million light-years apart in their original size. But the dark matter had not moved with the sound. It had stayed close to where it began, piled in the original wells of gravity. So, at the end of the ringing, the young universe held two overlapping patterns, the bright shell of ordinary matter sitting a great distance out, the quiet mound of dark matter still at the center. Two faint pictures, layered on top of each other, waiting to grow. Gravity does not care which kind of matter is which. It only cares about mass. And so, as time passed, both patterns began pulling on everything around them. The dark matter mounds drew in more dark matter. The bright shells drew in more gas. The two structures wove themselves together. Galaxies formed at both places, the center and the ring. This is why, when we map galaxies today, we find that faint extra chance of finding a companion galaxy at just that special distance. The song is preserved in the arrangement of the light. But the deeper skeleton, the true architecture of the cosmic web, was drawn by something that never sang. The question that still hangs over all of this is simple, and it is very old. What is the dark matter made of? One idea, the oldest, is that it is a heavy, slow-moving particle that barely feels any force except gravity. Another possibility is that it is an extremely light particle, so light that it behaves almost like a wave stretched across whole galaxies. Some researchers wonder if it is not a particle at all, but a sign that our theory of gravity itself is incomplete on the largest scales. Each of these ideas would leave a slightly different fingerprint on the frozen ripples. Each would shape the cosmic web in its own quiet way. The evidence so far cannot tell them apart. What we can say is this: the light of distant galaxies traces the ordinary matter the part that once glowed pink and rang like a bell. When we count galaxies at every separation, we see the faint bump left by the acoustic waves. But the shape of that bump, its exact height, its exact width, depends on how much dark matter was sitting quietly beneath the plasma, sculpting the wells the sound had to climb out of. By reading the bump carefully, we learn about the invisible partner. We learn a little more about the thing we cannot see. It is a strange kind of listening. We hear the song of the bright matter, and from the shape of the song, we guess at the weight of the silent listener standing beside it. The music tells us about the room. The room, in turn, tells us that most of what fills the universe is something we still cannot name. The cosmic web glows in soft threads of pale gold and deeper red wherever ordinary matter has gathered, and along those same threads, unseen, the dark matter runs like a colorless river, holding the shining strands in place. The light shows us the pattern. The darkness holds it steady, and somewhere in the space between them, an answer is still waiting. The old sound is still moving. That is the strange and beautiful thing to sit with tonight. The pressure waves that rang through the young universe never truly stopped. They froze into the arrangement of matter when the fog cleared, and then, along with everything else, they began to stretch. Space itself has been growing ever since. And as space grew, the ancient ring grew with it, pulled wider and wider, like a slow breath that never quite ends. To picture this, imagine a single ripple spreading across a pond. Now imagine the pond itself is quietly expanding under the ripple. The wave keeps its shape, but the distance between crest and crest grows with the water. In our universe, that expanding pond is space, and the ripple is the shell of matter left behind when the plasma cooled. Today, that shell sits at a scale of about 490 million light-years across. It was much smaller when it was first laid down. The stretching we measure between then and now is the fingerprint of something we still cannot fully explain. We call it dark energy, though the name mostly hides how little we understand. Dark energy is the quiet name we give to whatever is pushing galaxies apart, faster and faster. It is not a sound, but it changes the sound. It changes how far apart the frozen crests sit when we look at galaxies near us, compared to galaxies far away. Each shell of the old ripple, seen at a different age of the universe, holds a record of how quickly space was stretching at that time. In this way, the ancient echo becomes a kind of tape recorder. Each layer plays back the tempo of expansion during a different era. Astronomers listen to that tape by measuring the distances between galaxies with great care. They compare the width of the acoustic shell as it appeared when the universe was young to the width it shows now. The difference between those widths tells them how much space has stretched in between, and when they line up many measurements from many epochs, they can trace the pace of that stretching across billions of years. The tape is faint, the measurements are hard, but the story it seems to tell is that the expansion sped up somewhere along the way. Here, the mystery begins to hum. One idea is that dark energy is a constant, a steady pressure baked into the vacuum of space itself. In this view, the ancient shell stretches at a smooth, predictable rate, and the acoustic ruler behaves exactly as expected. Another idea is that dark energy is not constant at all. It may have shifted in strength as the universe aged, growing or fading in ways we have not measured well. If that is true, then the old ripple would be stretched unevenly across time, its width slightly off from what a simple model predicts. Recent surveys have hinted at small differences between the ruler's expected size and its measured size at different distances. Some researchers wonder whether these tiny mismatches are simply noise, the natural scatter of hard measurements. Others wonder if they are the first quiet signs that dark energy is changing. The evidence is not yet strong enough to say. Both possibilities remain open, and the debate is soft and ongoing, the way debates in cosmology often are. There is a poetic quality to the situation. The oldest sound in existence has become the tool we use to study the newest and strangest force in physics. A ripple that stopped ringing almost 14 billion years ago is still telling us how the universe behaves today. Its wavelength has been stretched by whatever dark energy is, and by reading that stretch we are, in a sense, listening to the shape of the unknown. If you converted the frozen ripple's scale into a tone, it would be far, far below anything a human ear could catch. Not a note, but a slow swell across cosmic time. Even so, instruments can turn its pattern into sound, and when they do, it comes out as a low, gentle throb, like a heartbeat measured in eons. That heartbeat is stretching. It is a little slower each billion years, in the sense that its crests move a little farther apart, and we do not yet know why the stretching happens at the rate it does, or whether that rate has always been the same. So the old bell no longer rings, but its shape is still being pulled outward by a force we have named, but not understood. The ancient echo has become a ruler for measuring a mystery, and tonight it keeps stretching, quietly, gently, while we listen for what it might one day tell us. Behind every ripple in the ancient sky lies a set of numbers so simple they feel almost like music. The early universe obeyed a small handful of rules, and from those rules came the whole pattern of galaxies we see today. Sound moved through the young plasma at a speed we can write down in one line. In that hot fog, the speed of sound was close to the speed of light, divided by the square root of 3. That is roughly 57% of light speed, an astonishing pace for a pressure wave. But the fog was so dense with radiation that pressure raced through it almost as fast as light itself. From that one number, everything else unfolds. If you know how fast the waves moved, and you know how long they had to travel before the fog cleared, you can multiply those two things together. The answer is the size of the largest ripple that ever formed. In today's stretched-out universe, that ripple sits at about 490 million light-years across. Every galaxy survey we build finds a faint extra clustering at that same distance. The ruler is elegant, and it is the same everywhere we look. The math behind the ripples is a set of gentle equations describing three things pushing on each other. Gravity pulls matter inward. Radiation pushes outward. Space itself expands, stretching every wavelength as time goes on. Physicists write these down as coupled equations, one for the density of matter, one for the density of light, one for the geometry of space. When you solve them together, you get a series of peaks and troughs in how galaxies cluster, spaced in a pattern that looks almost like harmonics on a plucked string. That pattern of peaks is where competing ideas begin to whisper. In the most common picture, the first ripples began as tiny bumps, left behind by inflation. The brief burst of stretching that some researchers believe happened in the universe's first fraction of a second. In that picture, the bumps were nearly the same size at every scale, a smooth, even hiss of noise across all wavelengths. The math predicts a very specific ratio between the heights of the peaks in the sky, and so far, the sky mostly agrees. Other researchers wonder whether the first ripples came from something else entirely. One old idea, once quite popular, was that networks of cosmic strings, thin defects in the fabric of space, could have seeded the ripples instead. That model predicted a very different pattern of peaks, more jagged and less musical. When the sky maps came in, The smooth pattern won, and the string models fell out of favor. Yet a small role for such defects has never been fully ruled out. There are still open questions inside the winning picture. Some models of inflation predict that the ripples should be almost exactly the same at every scale, with a number called the spectral index sitting at 1. Measurements find a value close to 0.965, a tiny tilt away from perfect flatness. That small tilt is one of the most precious numbers in cosmology. It hints at how long inflation lasted and how fast it ended. But the same tilt can be produced by many different models, and we cannot yet tell which one nature actually used. The math of the acoustic peaks also holds a puzzle called the sound horizon. That is the distance the pressure waves managed to travel before the fog cleared, measured in the units of the young universe. Its value is around 150 million light-years in those early terms, later stretched by expansion to the larger figure we measure today. Different ways of pinning it down give slightly different answers. Some researchers wonder whether new physics between the early and late universe has quietly nudged the ruler by a small amount. Others believe the numbers will fall into line once our measurements grow sharper. What ties all of this together is how few ingredients the math really needs. A speed of sound, a moment of release, a rate of expansion, a tilt in the initial hiss. From those few numbers, the whole cosmic web unfolds, filaments and voids and clusters and walls, all arranged around a soft echo 500 million light-years wide. The equations fit on a single page. The universe they describe fills every direction we look. Whether those simple rules are the whole story or only the surface of something deeper is one of the quiet questions that keeps this field alive. The math is beautiful. The math is also incomplete. Somewhere between those two truths, the ripples keep humming, patient as ever, waiting for us to listen a little more closely. Before there were sound waves, there was something even quieter, a stretch, a smoothing, a moment so brief and so strange that we still argue about what it was and whether it happened at all. The leading idea is called inflation, and it proposes that in the first tiny fraction of a second, the universe grew faster than anything has grown since. In that impossibly short breath, the cosmos is thought to have doubled in size again and again, taking a speck smaller than an atom and stretching it into a region larger than everything we can now see. If inflation truly happened, it set the stage for every sound the young universe would later sing. The pressure waves we have been listening to across these long hours would have started as tiny wrinkles inside that stretching, quantum jitters, so small they are hard to picture, would have been pulled outward until they became gentle bumps in the density of the newborn cosmos. Those bumps then rang. They pushed and pulled. They became the notes that froze into the cosmic web. That story is elegant, and much of the data seems to fit it. Yet inflation itself remains an idea, not a proven event. We have no direct recording of the stretching. We only see its possible fingerprints, softly pressed into the light and the matter that came after. The delicate part is this: for the universe to look the way it does, the initial ripples had to be tuned within a very narrow range. Too smooth, and gravity would have had nothing to grip. No stars would have formed. No galaxies, no filaments of glowing matter draped across the dark. Too rough, and the young cosmos would have collapsed into a rubble of black holes long before any planet could cool. The ripples we infer from the ancient light sit in a soft middle place, gentle enough to allow slow growth, strong enough to eventually gather matter into the shapes we see. Why the middle place? That is one of the deepest open questions in all of physics. Some researchers think inflation naturally produces this balance, and that the numbers we measure are exactly what a simple stretching phase would leave behind. Others are less sure. There are many possible flavors of inflation, and each predicts a slightly different pattern of ripples. Some predict extra tilts. Some predict small bursts of extra bumps at certain sizes. Some predict faint twists in the polarization of the ancient light that we have not yet detected. The data we have cannot yet tell these versions apart. There are also thinkers who wonder if inflation happened at all. One competing idea imagines a slow bounce instead of a sudden stretch, where an older universe collapsed and rebounded into ours, laying down its own pattern of ripples in the process. Another proposes that the early cosmos passed through a strange phase in which sound waves themselves set the scale of the first bumps, without any stretching at all. Each of these ideas can be tuned to match what we currently see. Each of them fails or succeeds in slightly different ways when pressed against the fine details of the sky. What is remarkable and worth resting inside for a moment is how narrow the window is. Change the strength of the first ripples by a small amount, and the cosmic web unravels. Change the balance between matter and radiation, and the sound waves ring at a different pitch, leaving a ruler in the sky that no longer matches what we measure. Change the amount of dark matter, and the peaks in the ancient glow slide out of place. Every part of the song depends on every other part. We do not know why the settings sit where they sit. We do not know if some deeper law forces them into this arrangement, or if there are countless other universes with different settings, and we simply live in one where the notes happen to line up. That second idea, sometimes called the multiverse, is not something we can test directly, and many researchers treat it with careful skepticism. It remains a thought, not a finding. For tonight, it is enough to notice the fragility. A whisper at the very beginning, quieter than any sound we know how to imagine, seems to have set the pitch for everything that followed. The ringing plasma, the frozen ripples, the great web of galaxies, the slow drift of light across billions of years. All of it hangs from that first faint breath. And whether that breath was inflation or a bounce, or something we have not yet dreamed, the question stays open, soft, and waiting in the dark. There is a quiet ache at the heart of this whole story. The sounds that shape the cosmic web are gone. They fell silent when the universe was only a few 100,000 years old, and they will never ring again. What we have left are the frozen shapes they carved into matter, spread across billions of light years, waiting for us to notice them. And even now, after decades of careful listening, we are still not sure what many of those shapes are trying to tell us. One of the deepest open questions is simple to state and stubborn to answer. Why do different measurements of the same ancient ruler give slightly different answers? When we measure the acoustic scale, using the faint glow of the early universe, we get one number. When we measure it using galaxies scattered across the sky today, we get a number that is close, but not quite the same. The difference is small. It is also refusing to go away. Some researchers think the mismatch is a hint of new physics between then and now. Perhaps dark energy behaved differently in the past. Perhaps a form of energy we have not yet named came and went in the early universe, briefly changing how fast space stretched. Others suspect the answer is more modest. Perhaps our galaxy surveys carry small errors we have not fully found. Perhaps our models of the early plasma are missing a subtle ingredient. Both possibilities remain alive, and neither has been ruled out. There is also the puzzle of how faithfully the ruler has survived its long journey through time. The acoustic scale was set in a nearly perfect fog. Since then, it has passed through galaxies, gas clouds, gravitational pulls, and the slow stretching of space itself. In principle, all of these effects can be modeled. In practice, we cannot be certain we have caught every distortion. A small unseen bias could shift our answers just enough to matter. Another gap sits in the smallest details of the sound. The peaks we see in galaxy maps are broad and soft, worn down by billions of years of gravitational shuffling. Some of the finer notes, the higher harmonics that once sang alongside the main tone, may be lost forever beneath that noise. If they carried extra information about the earliest fractions of a second, that information may now be hidden past the point of recovery. We may hear the melody, but never the full chord. The role of dark matter also holds quiet mysteries. It shaped the sound waves without ever singing along, and it still shapes the web today. If dark matter is more than one kind of particle, or if it interacts with itself in ways we have not detected, the imprint on the acoustic pattern could be subtly different from what our simple models predict. So far, the differences would be small. Small differences, though, are exactly what could tip us toward a new understanding of what most of the universe is made of. There is a stranger gap as well. We do not know if the initial ripples were perfectly random. Standard theory says they were, arising from tiny quantum fluctuations stretched to enormous size. Some ideas suggest there might be faint patterns hidden in those first ripples, echoes of physics that happened before inflation, or of processes we cannot yet name. If such patterns exist, they would show up as gentle asymmetries in the frozen sound. So far, no clear sign of them has been found. The search is not over. And then there is the largest question of all, the one that sits behind every other. We do not know whether the story we tell about the acoustic waves is complete. It fits the data beautifully. It predicts things that later turned out to be true. Yet the universe has a long history of appearing simple until we look more closely. A future survey could reveal a feature that no current model expects. A single unexpected bump in the pattern could send us back to the drawing board with a kind of joy. For tonight, though, the mystery is enough. The sounds are gone. The ruler is stretched and softened and dimmed. Our measurements almost agree, and their small disagreement may be the whisper of something we have not yet learned to hear. There is no rush to solve it. The waves have already done their work. They have shaped the vast, delicate web that holds every galaxy you will ever see. The remaining questions are gifts in a way. They tell us the story is not finished. They tell us that somewhere in the quiet numbers, a new chapter is waiting, and they invite us to keep listening, gently, patiently, to a universe that has already stopped ringing, but has not yet stopped speaking. The instruments we use today to listen for the ancient ringing are already remarkable, but they are only the beginning. In the years ahead, new telescopes will open their wide eyes and try to hear the faint notes we have missed. Some sit on mountaintops in the dry, high deserts, where the air is thin and the sky is very dark. Others float in space, drifting far from the noise and glow of our home planet. Each one is designed to map more galaxies across more of the sky and further back in time than anything before. One instrument, now scanning the heavens, uses thousands of tiny fiber optic eyes, each one aimed at a single distant galaxy. It gathers light from millions of them, night after night, quietly building the largest three-dimensional map of the universe ever made. Within that map, researchers hope to trace the faint bump left by the frozen sound wave, with sharper edges than we have ever seen. A cleaner edge on the ruler means a cleaner measurement of how fast the universe is stretching. And that, in turn, might finally settle the disagreement between different ways of measuring cosmic expansion. Other future observatories We'll hunt for the ripples in a different way, radio arrays, spread across whole continents. We'll listen for the soft hum of hydrogen gas from the young universe. Hydrogen, the simplest atom, gives off a very faint radio glow, and by mapping that glow across billions of light years, researchers can trace the same ancient pattern of peaks and valleys. This method, called intensity mapping, does not need to see individual galaxies at all. It only needs to hear the overall song of gas spread thin across the cosmic web. Space-based telescopes will join the search too. One will survey a huge fraction of the sky in infrared light, catching the glow of galaxies whose ancient light has been stretched into wavelengths our eyes cannot see. Another will focus on smaller patches with extreme precision, measuring the shapes of distant galaxies to see how their light has been gently bent by unseen matter. Together, they should trace the frozen sound wave across more cosmic history than we have ever managed to reach. What might all this new listening reveal? One hope is that the different measurements will finally agree, and the ruler will click into place. If that happens, we will know the expansion rate of the universe with a confidence we do not have today. Another hope is that the disagreement will sharpen instead of fading. That would be strange in a beautiful way. It would mean the ruler itself is telling us that something in the standard picture of the cosmos is not quite right. Some researchers wonder whether new kinds of particles or new behaviors of dark energy will show up in the fine details of the peak. Others think the answer will be more modest, hidden in small measurement errors that today's instruments cannot fully control. Both possibilities remain open. The truth may be a blend of both, or something no one has yet imagined. Now let your mind drift outward, past our own moment, into the long, slow future. In 1 million years, the constellations we know will have shifted into shapes no one alive today would recognize. In 1 billion years, the sun will have grown warmer, and the oceans of our world may already be gone. Continents will have drifted together and apart. Stars we see clearly tonight will have burned through their fuel, while others, still forming inside quiet clouds of gas, will shine for the first time. Yet the frozen sound wave will still be there. Its ripples, stretched even wider by then, will still shape where galaxies gather and where the great voids yawn open. The web will thin as space keeps expanding, and distant galaxies will drift further from view. In the very deep future, so far ahead that even the word future feels small, other galaxies may fall out of reach entirely, leaving whoever remains with only local skies to study. If any minds exist in that far era, they may look back at our time as the golden age of cosmology, when the ancient ringing was still readable, when the ruler still lay across a sky full of visible galaxies. Or they may find new ways to listen that we cannot picture from here. The universe keeps becoming something new, and each new form carries traces of what came before. The waves that shaped the web will echo in the arrangement of matter long after their sound has faded past all hearing. What those traces will mean to future eyes remains, for now, another quiet open question. Step back for a moment. Let your view widen until the whole night sky becomes a single, soft image in your mind. Every point of light out there, every galaxy, every quiet filament of glowing gas sits along a pattern that was shaped by sound. Not sound as we know it, with ears and air, but pressure moving through a hot young sea of light and matter. That ancient song is still there in the arrangement of things. It is the reason the sky is not smooth. There is something gentle about knowing this. The universe did not grow into its shape by accident. It grew along ripples, and those ripples were music of a kind, waves that spread out at close to the speed of light, before falling silent forever. Every galaxy we can name, every star we can point to, sits somewhere on the frozen surface of that old song. The cosmic web is a kind of sheet music that no one can quite finish reading. The wonder is that we are part of it. The atoms in your hands were once inside that hot fog. The oxygen you're breathing came from stars that formed inside the denser knots of the web. The calcium in your bones was cooked in old suns that lived and died along those ancient filaments. The iron in your blood traveled through space for billions of years before settling into the rock that became this planet. In a very literal way, the sound waves that shaped the cosmic web also helped shape you. And yet, for all this closeness, the web still refuses to tell us some of its secrets. The ruler it left behind is beautifully clear in the largest surveys, and beautifully stubborn when we press it for a final answer. It gives one number for the expansion of the universe. Other methods give another. The gap is small, but it will not close. Some researchers think the ruler itself is fine, and something odd happened in the local universe. Others think the ruler is being bent by physics we have not yet named. The web knows, and it is not saying. There is a quiet humility in this. We can map billions of galaxies. We can measure a ripple that stretches 500 million light years across. We can trace it back to a moment when the universe was only a few 100,000 years old, and still the pattern holds back a piece of itself. It hints that our picture of matter and energy is not quite complete. It suggests, softly, that something is missing from the story. That missing something might be a new kind of particle, drifting through the void without ever touching light. It might be a subtle change in how gravity behaves over long distances. It might be a wrinkle in the very early moments, before the sound even began. Every theory has admirers, every theory has doubters, and the web sits above all of them, ancient and patient, waiting for us to grow into a better question. There is comfort in unsolved things. A universe that gave up all its secrets would be a smaller universe. The cosmic web reminds us that curiosity is not a stage we pass through on the way to knowing. It is a permanent condition of being alive under a sky this deep. Somewhere out there, a filament of galaxies is drifting apart along the ghost of a wave that fell silent before Earth existed. And somewhere down here, a mind made of star stuff is thinking about it. You are, in a sense, the universe listening to its own old music. The atoms that make up your thoughts were once part of the pressure that carried those waves. The carbon in your cells rode inside stars that formed at the crossings of the web. The water in your body traces back to ice that clung to grains of dust in the filaments. Nothing about you is separate from the pattern. You are one more small brightness, sitting along a ripple that has been spreading for nearly 14 billion years. Maybe that is the deepest thing the web has to offer. Not an answer, not a final map, just a sense of belonging to something enormous and quiet and still unfolding. The mystery of how sound became structure, of how a ringing plasma became galaxies and planets and people, is a mystery we may never fully solve. And that is not a loss. It is an invitation. Every generation gets to lean into the same soft question and hear a slightly different echo. Tonight, you are one of those listeners, warm, safe, half asleep, held inside a pattern older than the stars. And so, we come to the end of our long, slow walk through an ancient song. The stars outside your window are still there, turning quietly on their invisible track. The great web of galaxies is still stretching, still humming with the memory of a sound that once filled everything. And you are still here, resting, breathing, held gently by a universe that has been rippling for nearly 14 billion years to bring you this exact quiet moment. Picture a small blue world spinning slowly in the dark. Half of it is turned toward its star, warm and bright. The other half is turned toward the deep sky, cool and calm. Somewhere on the night side, an ocean rests under a soft moon. Waves move across it in long, patient lines. They carry no urgency. They only carry themselves, the way sound once carried itself across the young cosmos. Those ocean waves are cousins of the ones we have been listening for tonight. They rise, they fall, they leave faint shapes on the sand. The pressure waves of the infant universe did the same thing, only on a scale so vast that a single ripple stretches across 500 million light years. Both are simply matter moving in patterns. Both are the universe finding a rhythm. There is something soft about knowing that the largest structures we can see were shaped by something as gentle as sound. Not explosions, not violence, just pressure, pushing outward, meeting resistance, pushing back, a slow breathing in and out of light and matter, until the moment the fog cleared and the breath was held forever. The galaxies remember. They stand in loose rings around the places where the sound waves stopped. They cluster along filaments the way dew clusters along a spider's thread, and we, tiny observers on a small warm rock, have learned to read the pattern. We have learned to hear an echo that no longer makes a noise. What remains unknown is still beautiful. We do not yet fully understand why different measurements of the cosmic ruler disagree by small, stubborn amounts. We do not yet know whether some hidden physics has bent the ruler between then and now. We do not know what dark matter is, or what dark energy is, or whether the first faint whisper before the sound began was truly the stretching breath of inflation, or something else entirely. These questions are not problems. They are invitations. They are reasons to keep looking up. Somewhere tonight, a telescope on a cold mountain is opening its shutter. Somewhere, a satellite is drifting through the deep quiet, collecting light that left its source before humans existed. Somewhere, a researcher is asleep at her desk, dreaming of the pattern she almost saw in her data. The listening continues, gently, without hurry, in 100 small rooms across the world, and you are part of that listening simply by wondering. The universe does not need us to understand it in order to keep singing, but it seems to have made us anyway, small, warm creatures, capable of asking why. That may be the softest mystery of all. Let the picture settle now. A calm ocean under a pale moon. A slow galaxy turning like a wheel of milk in the dark. A web of light so wide that a single one of its threads would take 100 million years to cross. And inside all of it, you, breathing, resting, safe in a room that is itself resting inside a planet, inside a solar system, inside a spiral arm, inside a galaxy, inside a cluster, inside a web that still remembers the sound. Nothing you need to solve tonight. Nothing you need to hold. The great questions will still be here in the morning. The cosmic web will still be humming its silent, frozen song. The telescopes will still be listening on your behalf while you sleep. We may learn the answers in our lifetime. We may not. Some mysteries are the kind you carry with you, warm and patient, for as long as you are here to carry them. Tonight, it is enough to have listened. Tonight, it is enough to have wondered. Tonight, it is enough to lie still and feel yourself part of something ancient and gentle and impossibly large. Rest now. Let your breathing slow to match the long, slow breath of the early cosmos. Let your thoughts drift outward, past the ceiling, past the sky, past the stars, into the soft, dark, where the sound once traveled. You are welcome there. You have always been welcome there. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.